Welcome to Lesson 2 of the Fizzy Foamy Fluids tutorial. In this lesson, we're going to tweak some of the attributes in our simulation to try and match the look of champagne pouring into a glass. One thing that's really important to consider when you're doing any sort of simulation or trying to match any sort of real-world effect or even going for more stylized looks is looking at reference. I recommend looking at different video reference you can find on YouTube or even on stock footage websites. They have wide libraries that are really easy to search and find high-quality videos of anything you might be looking for. For example, I found this footage on a stock website where you can see champagne being poured into a glass and you can get an idea of the amount of motion and the bubbles and the foam rising in the glass. There's a lot of variation between champagne being poured into a glass and just liquid in general, and you can kind of take liberty when it comes to certain motion. Of course, you want to get the general motion of the fluid being poured in, this swirliness and rising bubbles, but you can see in this footage there's a lot less foam than the previous one. And I kind of like this look better, so this is the kind of foam that I'm going to aim for in our simulation. Now that we've taken a look at some reference, we know what we're aiming for as far as the motion of our overall simulation. Before we start tweaking anything too much, I want to go to the flip solver, go to volume motion, volume limits, and I want to change this default size. So at default, the box size is 50 in each direction, and that refers to Houdini units, which if you remember from our previous video, are meters. So this is saying that the box that the simulation is contained in is 50 meters in each direction, which is way bigger than we need. So we're going to turn that way down. I'm going to change it to about half a meter in each direction, which still, we don't quite need this much space, but it's a lot better than having it 50 in every direction. And the reason this box size matters is because the box that we're changing here is basically the box that the solver is using to know what it should be taking care of. So anything inside the box is what it's trying to solve for. We don't need it to be running any calculations for that amount of space. If you pan out slightly, you can see this light-colored box. This is our bounding box, essentially, for our solver. And you can see that our box center is at the origin, which is causing our emitter to be a little outside the box. So I'm just going to move up the center so that it is at the origin. We're still containing our simulation without it being ridiculously large. With the box size out of the way, we can go ahead and take a look at how our simulation looks before tweaking any attributes. And we're going to do that by just running a flipbook real quick. So immediately you'll see that it's actually kind of hard to parse what's going on in our play blast. Our simulation is pretty low resolution, and because of that we can't really see any detail in our simulation, and the whole thing is also moving pretty erratically. So to get a better look at what's actually going on in the simulation, we're going to reduce the particle separation. We'll go to our flip object, and we're going to change our particle separation to about half of what we currently have it at. So I'm going to change it to 1.5. Enter. Now when you reduce your particle separation, this is going to make your simulation slower because it's running a much higher resolution sim. And you might want to take that into account depending on how long it might take your machine to run a simulation. So while you're iterating over different attributes, different movement, you might want to have your particle separation a little bit higher just for quicker iteration time. So let's go ahead and flipbook this to see how it looks. So immediately you can see there's a lot more detail in our simulation. You can kind of tell what's going on, the different movement that's happening. It's still moving pretty erratically, but at least you can kind of see what's happening in your simulation. You may notice it also looks like we have less volume in our simulation compared to when the particle separation was higher. And the reason for that is when you reduce the particle separation, you're reducing the amount of distance between particles, between points. And since you reduce the distance between each point, it makes the fluid look a lot more compressed visually. In addition to the fluid compression, I'm also noticing in the first few frames when the fluid first hits the glass, we're seeing a little bit of intersection with our collision object. It's having a hard time calculating that first initial hit. One way to increase the overall volume of our fluid, as well as improve the way the fluid is colliding with our glass, we're going to go up to the sim itself on the DOP network. We'll go over to the simulation, and we're going to increase the sub-steps. I'm only going to increase them from 1 to 2. If you're not familiar with DOP network, substeps refers to the amount of times a simulation is run per frame. So increasing this to 2 means that it runs the calculations for the simulation twice per frame. And again, much like decreasing our particle separation, this will increase your overall simulation time, but it will increase the accuracy of your simulation. So let's go back into our DOP network. Let's check out what it looks like now. Immediately you can see that we're getting a lot more volume in our simulation. As I mentioned before, increasing our substeps means that it is calculating simulation twice per frame. This means that we're getting twice as many particles as we were previously. In addition to increase of the volume of our fluid, you can also see that our collision is moving a lot smoother. We're not having any sort of intersecting issues anymore. Now that it's calculating twice per frame, it's creating a much more accurate collision interaction. One thing you might notice is that the overall motion is still pretty erratic. The fluid's moving really fast, it's turning pretty wildly, and we want to smooth that out. So we're going to go to our flip solver in volume motion and velocity smoothing. Increasing this value causes the velocity of particles to smooth out as the particles start to share more of their velocity with their neighbors. You don't want to have too much smoothing or you'll start to lose the detail in your simulation. So let's increase it to something, say, about 0.4. And we'll run a flip book for that. Now that we've increased the velocity smoothing, you can see that our overall velocity is a lot less erratic without losing the overall motion of the fluid. Next, we'll be assigning our particles to foam and fluid groups and assigning them specific attributes to create a differentiation between them in the simulation. And to do that, we're actually going to use a pop group node. One thing to consider as we're messing with these different attributes and adjusting the overall motion of our simulation is that while this is a flip simulation, you have to keep in mind that these are still particles, these are still points, so we can still use all these nodes that you would normally see in a pop simulation. So I'm going to rename this node foam group, and I'm going to name the group foam. And then I'm going to check on preserve group. What this does is it makes sure that once a particle is part of the group, it stays in that group. So even if some sort of attribute that we're setting for it to become part of the group, if that changes along the way, it'll still remember this particle was in the group at one point, so it will stay there. And then I'm going to set up a custom rule for what points will be foam points. So under the rule tab, I'm going to enable it, and that'll make it so we can enter our own expression here. Take that out, and I'm going to type in group equals not ID mod 10. So basically what this will do is it'll take every 10th point, every 10th particle, and add it to the group. Then semicolon, and then we're going to hook it in down here into particle velocity, since this is affecting the particles. I'm going to set up a specific color for the group so that we can tell the difference between particles that are in the foam group and that aren't in the foam group. But before I do that, I'm going to go over to our flip object under guides, particles, where it says visualization type, and right now it's set to speed, which is what's causing it to have that blue to white ramp that you see whenever we run our flip books from down here. We're going to go ahead and set the visualization type to none so that it's not affecting the color attribute so that we can affect it with our own specific color. So to go ahead and start setting the color, I'm going to drop down a pop wrangle. I could do this with a simple pop color and just set it to a specific group, but I'm going to use a wrangle because I know I'm going to be changing a few different attributes for points that are in this group. So go ahead and plug it in, and I'll just change this to set attributes. So let's go ahead and set our default color. Let's just make it black. And then we'll go down, we'll say if at group foam. So if it's in our foam group, and if you use a different name, you just want to make sure that this part right here matches whatever you've called your group here, because that's what it's looking up. So if it's in the foam group, do a curly bracket, we'll set the color to white. Go ahead and hold Control Enter, or you can click this and that'll update your pop wrangle so that it's taking in whatever you've written in your expression. And let's go ahead and see what this looks like in a flipbook. So you can see that it's working as expected. It kind of has a salt and pepper look to it right now because the particles don't have any sort of attributes making their motion different from one another, but you can see that about every 10th particle is colored white because those particles are going to be part of our foam group. And if we feel like we have too many or too few of our particles in our foam group, we can always change this number to have a higher percentage of them landing in our foam group. And the main reason that I'm using an expression rather than the random function in the group is because I actually want to set a second condition for our group of particles. You can see in our flipbook that immediately there are foam particles at our initial pour, and I don't really want that. When you're pouring out the fluid from the actual bottle, you wouldn't expect to see foam already in the stream of fluid. You would expect the foam to start to form as it hits the bottom of the glass. I don't want our initial particles to be part of the foam group. So what I'm going to do is I'm going to go to our pop group where we have our expression for what particles end up in the group, and I'm going to set a second requirement for them to end up in the group by adding two and signs. That means that both statements here have to be true for them to land in the group. So it has to be every 10th particle, and the age has to be greater than, let's say, 0.4. So we can go ahead and run that and see if we notice a difference. So here you can see that we're not getting any foam particles until the fluid has already come down into the glass. This gives the impression that the foam is a result of all the turbulent motion from the champagne rather than it just existing as it pours out the bottle. I think that the foam takes a little too long, just a beat too long to appear, so I'm actually going to reduce the age requirement down to, let's say, 0.3 instead. Let's run that. Alright, that's feeling a lot better. The foam is appearing when we're hitting the bottom of the glass, but it isn't taking so long that it starts to feel like it's just switching on. Now we can start messing with the actual attributes that affect the overall motion of our two different groups, so we can start to see some differentiation between the foam and the fluid. So back in our pop wrangle, we can start to set up different attributes. The first attribute I'm going to set up is the density, so how dense each group of particles is. So I'm going to set that the default density, let's say that the default density is around 1000. And then the density for our foam particles, we want it to be something that's less dense than our fluid. So that causes it to rise to the top of our fluid. So let's do something drastically different. Let's do density equals 100. And let's see what this looks like. So it's kind of hard to see at the beginning of the simulation, but if we scrub to the end of frame 50 here, you can see that a lot of the foam has risen to the top because it's less dense than the fluid. One thing you might notice is that there are a few stray particles that kind of raise above as if they're kind of floating away because they're just so low density. So I'm actually going to increase their density a little while still keeping it below the overall fluid density. So I'm going to increase their density to 300. See how that looks. So again, it's kind of hard to see what's going on in the beginning part of the simulation, so we'll scrub towards the end of our playblast. And you can see we still have our particles rising towards the top, and I'm only playlasting the first 50 frames out of 120 is what I'm doing for the whole project. So what we're seeing is our simulations start to have the chance to settle since the pour has stopped. So I'm going to go ahead and flipbook the entirety of our simulation so that we get to see the interaction between our particle groups as it gets a chance to settle. Alright, so now we can actually see how the simulation is resolving. We're still having some fast velocities, a little too much swirly motion going on, but we can tamp that down later. What we're really trying to get a feel for is the difference in density between our two different particle groups, and you can see it pretty plainly. The foam particles are rising up to the top of the liquid. They seem to be a lot lighter. They just have a general upward motion on their own, which is definitely what we want. The next attribute we're going to set between the two groups is the viscosity. You might recall me mentioning earlier that water has very low viscosity value, and the champagne is basically going to act like water. So we're only going to set the viscosity to 1. However, for the foam, I actually want it to be more viscous than the fluid so that it kind of clumps together, sticks to itself, and has a little bit more of a lumpy motion to it instead of being really fluid. So let's change the viscosity of the foam points, and let's make it something a lot higher than 1. Let's go pretty high. Let's go 1500 just to see how that looks so we can see that everything's working and get a feel for what something more viscous feels like. So let's go ahead and flip book that. So you can start to see towards the end of our simulation, if we just scrub towards the end, the high viscosity value is causing all the points to kind of try to stick together more and have a general, more of a slow kind of blobby motion, which you might expect from a layer of foam. One thing I'm noticing though is that they kind of stick together a little too much, and they're kind of slowing down a little too much along the edge, where we have this kind of spinning motion from the swirling of the liquid. We can kind of see it's not moving as much on the top because of how viscous it is. Our results are getting a little bit stagnant towards the top compared to the bottom. And while these results might be fine on their own, there's a little bit too much of a disparity between these two groups right now. So I'm actually going to turn the viscosity down some to see how that looks. So let's change it down to about 1/3 of what it's at. And we'll run that and see how that looks. So here you can see we're still getting that clumping at the top of our simulation, but it's not slowing down too much. We're still getting a nice swirling motion that matches the general movement we're getting at the bottom of the simulation. And the last attribute we're going to change between these two groups is the divergence. Increasing the divergence attribute will essentially cause the particles to expand outwards, kind of creating the rising foam motion that we're looking for in our glass. So we'll go back to Houdini and we'll set our divergence value. Oops. Do at divergence equals 0. And the reason I'm setting this as a float rather than an integer is that this is a little bit more of a touchy attribute, where something that's above 1 might actually be pretty drastic. So just to show what that looks like and to get an idea of what divergence does, I am going to set it kind of high, just so you can see what it is divergence is doing in the simulation. So let's go ahead and run that. So immediately you can see we've got some sort of expanding motion, and it's also causing more turbulence down inside the liquid itself, because these particles that are towards the bottom of the glass are also expanding with the increased divergence attribute. So while it's nice that we're getting this rising foam up top, we have a little too much expansion going on overall, and it's causing a lot of turbulence within our glass. So I'm going to go ahead and turn the divergence down on our foam. Change it to something a lot lower, so about 0.25. So that way we're still getting some expanding motion without it overwhelming the simulation and causing a lot of turbulence. So go ahead and run that. So now that we've turned the divergence down, you can see that we're still getting the expanding motion towards the end of our simulation. It's pretty slight because the champagne, I don't expect the foam to overtake the rim of the glass. Maybe for something more like beer, you would expect foam to fill up the glass and maybe overflow. But for our purposes, this is a pretty good rate of expansion for our foam, while also keeping it from making the bottom too turbulent. One thing that's been pretty prevalent throughout all of our iterations is this really turbulent, swirly motion we have going on in our liquid. You can even see it a little bit towards the top of the foam at the end. And while it's great for the initial pour to have a lot of turbulence as it's first coming into the cup, we might want to tone down the overall velocity as it starts to settle towards the end. And we're going to do that with another wrangle. So we'll go down here, put down another pop wrangle. And I'm going to call this one reduce vel. And we're going to do exactly what it sounds like. We're basically going to just scale the velocity down over time. And the way we're going to do that is we're going to multiply the current velocity by a specific channel that we'll set. So I'm just going to call it mult for multiplier. Then I'm going to hit this to create the channel. So now we have our channel down here. And if it's set to 0 right now, our velocity is going to be times 0, so it's not going to do anything. I want to set this close to 1 because this value is going to be multiplied on each frame. So it's going to be the current velocity times this value per frame. And we want it to stay pretty similar to what we have now, but I do want it to decrease over time. So I'm going to set it to 0.97. So that means on each frame, the current velocity is going to be multiplied by 0.97. On the next frame, the value will be multiplied by 0.97 again. So over time, it's going to reduce the overall velocity, kind of smoothing out the turbulence we're seeing, but hopefully it won't be too jarring since it's pretty close to the value of 1. So let's go ahead and see how that looks. So now you can see immediately it's a lot less turbulent overall. We still kind of have a little bit of a jittery motion from our divergence, so we might want to look into changing that value some, or possibly the density or viscosity. These are all values you're just going to kind of have to tweak over time, see what looks best for your simulation. One thing I want to change about the parameter we just set up is I don't want to start reducing the velocity right from the get-go. Much like the foam grouping, I don't want it to affect new particles. So I'm going to add the condition that a particle must be over a certain age before it starts losing its velocity. So we'll go in here, and same deal as when we were creating the groups. So we'll do if age is greater than, say, 0.4. Do a curly bracket, and then we already have our function here. We'll just close it with another bracket, and let's see how that affects everything. That's starting to feel a lot better. We still have that initial turbulent motion when the fluid is first hitting the glass and kind of splashing back on itself. That part isn't getting slowed down anymore, so that's a lot nicer. But over time, as it settles, it becomes a lot less turbulent, which is what we want. And there's one more force I want to add in. You can see at the end of our simulation, we still have a fair amount of foam points towards the bottom of the glass, and they're just kind of swirling around with the liquid, which is fine, but I want them to have more of a buoyant feeling. I want to give them some force that pushes them upwards towards the top of the glass. So we're going to add in a force to do that for us. So I'm going to put down a pop force and plug it in. And I'm going to check on group, and I'm going to type in foam. So that way it'll only operate on our foam points. For the force value, we just want to push them up in Y. So we'll just change this to something like, let's say, 5. And let's see how that looks. So here you can see at the end of our simulation, we're getting a lot more upward motion. A lot more of the foam points end up at the top of our glass. One thing you might notice, though, is as the fluid was pouring in, all of the foam points are uniformly receiving the force of 5 upwards in the y-axis. And we might not really want that, especially not through the whole simulation, and not when they're already at the top of our glass. We don't want these particles to have an additional force, kind of forcing them almost separate from the liquid. So we're going to basically ramp our force value based on if the points are towards the bottom or towards the top of our glass. So that way the most force is applied to the points that are at the bottom and less force is applied to points that are already at the top where we want them. So what we're going to do is we're going to go to our pop force, and we're going to check on use expressions. That way we can go ahead and add an expression to our force value. So what we're going to do is we're going to type force, and we're going to multiply it by a ramp that we're going to set up. So we'll have a ramp attribute, and the value we want to ramp is actually the position in Y between a minimum and maximum value that we set. So I'm going to create a fit function, not a fer function, and we're going to fit the value at Y between a channel we'll call Y min and a channel we'll call Y max. And we're going to fit that from 0 to 1. So basically what this will do is it's fitting our current point position of Y between a minimum we'll set and a maximum we'll set. And when it's close to the minimum, it'll return 0, and when it's close to the maximum, it'll turn 1. And it creates the values between. So if it's somewhere in between these, it'll be, say, around 0.5. And then we're taking all of that information, the 0 to 1 value, and we're going to run it through a ramp. So that way we have even more control of the way the force is distributed across our particles. And just add one more parentheses, just to make sure that this is closed off. We scroll down past the noise options, and we can see we have Y min and Y max. And this is going to be referring to the minimum position and maximum position. And one quick way to go ahead and figure out approximately where that might be is we can just look on our actual glass object, and we can go select a point somewhere on it, and we can just go over to the geometry spreadsheet and show only selected. So now we can see all these attributes for the point we've selected. So this point towards the top of our glass is at 0.2. So let's go ahead and just put the Y max at 0.2. Let's go back up a level to our scene view. And let's go ahead and select the point at the bottom of the glass. So over to our spreadsheet again, and that's at 0.09. And we don't have to be this exact with it. These might be values we want to tweak a little bit, but this is a good, quick way to go ahead and grab the min and max values for our glass. So now, at default, a ramp is also going to give out a 0 to 1 value, and we can just swap these. We can give this end a value of 1 and this end a value of 0. You can also click to add new points inside your ramp so that you can have a really specific custom curve for the way the fall-off value would work. And you can change the interpolation to further customize your ramp. For now, I'm actually just going to leave it at the default, just kind of a linear 1 to 0. And let's go ahead and see how that looks. So now you can see that we're getting that nice upward motion towards the bottom of the glass. Our particles are rising up to join the top, but we're not getting too much jittering at the top, and these particles aren't receiving any sort of additional force that's pushing them out. Now there's definitely lots of little things you might notice in your simulation. Still a little bit of jittering towards the top. Maybe we need to increase the viscosity, reduce the density, increase the density. All these values you can kind of play with until you have a simulation you like. But I'm pretty happy with how our simulation's looking right now. We might have a few trouble particles, but we're going to look into ways we can deal with a few stray particles after we've simulated something. So once you're happy with the simulation you have, if you've been working at a higher particle separation, you might want to reduce it for your final cache. Also keeping in mind that when you reduce your particle separation, you might have a visually compressed look as all the particles are more tightly packed together. So you want to keep that in mind as you're changing your particle separation. So once you're happy with your simulation, you just go up a level, out here where we can see our DOP network. I'm going to go ahead and change this back to primitives just so we don't see the dots displayed all along our geometry. So I'm going to put down a DOP IO to grab our particles. And for our DOP network is you can just click and hold, and you can actually drag it up here to our DOP network. And then I'm just going to copy this down to here for our DOP node, and I'm going to grab our fluid objects. So now it's pointing to our dot network and specifically our fluid object. Then you can go ahead and go to the presets and you can select flip fluid, and it'll automatically set up some fields for you so it knows what it is you'll probably want to import when it comes to flip simulations. And if we display that, we can see that we're importing the points from our simulation, bringing them in. It's the same as what we were experiencing in our play blasts. So to cache it out, you can just put down a file cache. And this is really personal preference, personal workflow, how it is you prefer to have your files organized. For me personally, I don't prefer to have a file name dependent on the name of our current HIP file, because I frequently will change the name of a HIP file, version up a HIP file, and I might have a lot of things going on upstream that are relying on caches from previous HIP files, and I don't like having to reconnect that. So what I prefer to do is, instead of the HIP name, I just do $OS, and I put another slash here for another directory. So the way I organize my geometry is we have our geo folder, and then I'll have a folder that matches the name of our current operator. So I'm just going to rename this to main sim, and I'm going to call it VO1. This is how I control my versioning, so I just have to keep track of the current version I'm caching out. So this is something I have to change manually. I have to just, when I do a new version, remember to do version 2, which might not work for some people. Maybe you need something that does rely on versioning up in your HIP file. But for me, this is how I prefer to work. So I just have it writing out to what will be mainsimvo1 and then mainsimvo1.frame.bgo. And then after that, it's as simple as saving to disk and then checking to load from disk so that it's loading the files you cache out. Alright, I've gone ahead and cut ahead where I've already cached out my sim, so we can easily scrub through our timeline and see our simulation without having to wait for it to calculate all of that different data. So now that we have our points, I mentioned earlier that we have some stray particles that we might want to get rid of, and we don't necessarily have to try to fix those in the simulation itself because we can just remove them after the simulation. Now at default, when you blast points in Houdini, it usually picks them up based on its point num, so whichever number point it is on the current frame. And as you might expect, the number of points is not consistent in a flip sim. It's changing as new points are emitted or points are created to fill empty spaces. And this is where ID comes in. Since we turned on the ID attribute in our simulation, each point has a unique integer ID attribute. And we're going to use this to blast the points instead of point num. There are a couple of different ways to do this, but one of the quicker ways to do this is to simply go into selection mode, so hit S, go over to the points so that we're selecting points, and then go over here and turn on groups. So it'll show you groups at first, so you can have, like, we have our phone group here that it'll show us. But up here where it has the little asterisk, if we do @ID and hit enter, it's going to show the ID values for our points. So you can see we have all these different IDs for every single point that's on screen. So now, if we select, I'm going to switch over to the lasso tool for easier selection. You can select points, and it's selecting these points based on their ID, which you can see over here in the box. It has these points highlighted because these are the ones selected. Then it's as simple as hitting delete, and that'll create a blast that is automatically using the ID attribute since we had it set up in our viewport. And it's blasted those stray points, so now when we scrub back and forth, we can see the ones we blasted are staying gone. And just for reference, so you can see how it would work normally if we hadn't set up this ID attribute. So I'm going to turn off group selection, and I'm just going to group those same points, hit blast, and it looks the same right now on our new blast, but this is just based on point num. So it looks the same on this frame, but if we go between the different frames, you can see they automatically pop back on because their point number changes on each frame, which is why we want to do this ID method instead. So I'm going to go ahead and delete this other blast. So with our ID method, I'm going to turn this back on so we can see our IDs. We can also add points to the selection pretty easily. So if we scrub back, we can see if there's some more points I want to get rid of. So I just hit this little arrow here to add to our current selection. and hold shift so it doesn't deselect our previous points, and hit enter. So now it's added those to our list of IDs. So you can just quickly scrub through your simulation and find any points that you want to get rid of, and just go ahead and grab those. So now we don't have any of those flyaway particles. I might end up deleting some points in here, but we can do that later on. We'll see how this looks when it's meshed out. But this is the quick way to go ahead and grab points based on their ID. So now that we've gotten rid of some of those stray particles we were seeing, we can go ahead and uncheck these just so it's easier to see what's going on. And I'm just going to rename this to Blast Stray Particles. And the next tweak I want to make is actually a tweak to the pour itself. So here you can see it's pouring straight down. It's a little bit linear. And I kind of want to add a little bit of a curve to this. Now this is something you could try to do in your simulation, have like a specific velocity coming from your source where it's kind of emitting out to the side as well as down. But that might take a lot of tweaking, a lot of iterating, and it might be quicker to go ahead and just push it a little bit to the side post-simulation. So the way I'm going to do that is first I'm going to isolate the newest points so that it's only affecting the points that are new that are currently pouring straight down. So I'm going to do that by putting down a wrangle. And I'm going to call this isolate new points. And at default I'm going to create a group called bend, and it's going to be set to 0, so that means there's a group that exists called bend, but none of the points are currently in that group. And then I'm going to create an if statement to create a condition for the points to end up in the group, and I'm going to do it based on age again, so that way only the new particles are going to end up in the group. And I only want this to affect particles that are pretty new, that haven't even hit the glass yet, that are still coming down from the pour. So I'm going to do a pretty low value, say 0.125, do a curly bracket, and at group bend equals 1. Oop, do another curly bracket. There we go. And so this means that particles that are less than this age value will be added to the group called bend. And so we can easily visualize it and start working with those points. I'm going to put down a split. And I'm going to grab the group bend. A split has two outputs. One outputs the group you've specified, the group you've selected, and one outputs the rest of the points that aren't currently selected, so the points that are not in our group. So if we display it, it's going to show us the first output, which is our bend points. So you can scrub through and see we're just getting those points that are pretty fresh to our simulation that aren't interacting with the glass too much. There's a little bit down here, but that's fine. So what we're going to do to bend these points is we're actually going to do a lattice deform. So to do that, we'll put down a lattice. And this is the geometry we want to deform. And this is just, again, personal preference, but if you hit Shift S, it'll change the shape of your network connections to make a little bit more of a curved look instead of that linear look, so it's just a little easier to look at for me. So now that we have our lattice, we've input the geometry we want to deform, and we need the rest geometry, and we want the deformed geometry. So our rest geometry is basically a reference point for the deformation. So it's going to need to be a frozen frame. So we're going to do that with a time shift. And we want to pick a frame where we have a decent amount of particles already there. So we don't want to do the very first frame because then it doesn't have much information to work with. So I'm going to set it to, I'm going to break this connection with Control Shift and set it to frame 4. So now we have a decent amount of particles. It's kind of a good midpoint. So it's stuck on frame 4. And then I'm going to put down a box. This is going to act as our lattice structure that we're going to deform. Let's go ahead and display the box, and let's go ahead and plug it into our rest geometry and our deformed geometry right now. So if we go to our lattice node, immediately you'll see it's throwing an error, and the reason for that is the divisions on the lattice node need to match our box divisions. Check on divisions for our box, and at default 3x3 matches the 3x3 here, but I'm going to go ahead and connect these because I know I'm going to increase the divisions on our box. So I'm going to go to our box, copy parameter, go to our lattice, and paste relative references. So that way it updates when we change the number of divisions on our box. So now if we pan up, we can get a better look at what we're working with. So right now it's not doing any deformation because we haven't changed anything between the rest geometry and the deformed geometry. So for the deformed geometry, what I actually want to do is just deform part of the box. I'm going to give the box a couple more divisions so that we have more to work with. So let's give this divisions of 5. And we actually don't need as many divisions here and here. We are mostly dealing with the divisions in the y-axis. So let's put down a transform, plug that in, and have this be our deformed geometry. So on our transform, we're only going to move some of the points. So we're going to select those points, go to point mode, and I just want to select these top points here. So go ahead and hit enter when those are selected. And then I'm just going to translate them a little bit to the side. I'm just going to pull it to the side. Let's go back to our camera view. So now if we go to our lattice node, let's go back to this so we don't see all the points selected. You can see we're getting a little bit of a bend here. So if we were to bypass this, we can see what it looked like originally, and we're getting a little bit of a bend, so we can kind of imagine that it's kind of coming out at the end of a bottle now. And we can kind of tweak this value. You can push it further, push it less. Obviously, if you push it too much, it's going to look really distorted. But this is something you can kind of just mess with a little bit. You can also change what frame you've time shifted on. So you can see how that might look if we use a different frame as the reference point. But I kind of like our current setup using frame 4, and I've moved it over 0.04 in the x-axis. So now we have a nice little curve to our points. And I'm going to go ahead and merge these bent points back together with the points that were not bent on the, and we can grab that from our split node from the second input. So now we've merged these points back together, and we have this nice little curve shape. So now that we've done some post-simulation tweaks, deleting straight particles and adding a little bit of deformation to our sim, we're going to split the foam and fluid points to start working with them independently. In the next video, we'll start working with the foam, do some additional tweaks to it to give us something we can render.